In the blink of an eye, 4 billion years unfold. The Earth's timeline and epic history. Look up at the night sky. On a clear night, the cosmos stretches out before us, a seemingly infinite tapestry of stars and galaxies. But within this vast expanse lies a place unlike any other, our home, planet Earth. A blue marble, suspended in the blackness, teeming with life, sculpted by forces that have been at play for billions of years. But Earth wasn't always this way. Its story is one of cosmic violence, fiery beginnings, and a gradual, almost miraculous transformation. This is the story of how our planet was born, a tale written in the very fabric of the universe, a journey that began from the ashes of stars. To understand Earth's genesis, we need to journey way back to the very beginning. Around 13.8 billion years ago, the universe as we know it didn't exist. Instead, everything was compressed into an incredibly hot, dense point. Then, in a moment we call the Big Bang, it all began to expand rapidly, violently, creating space and time itself. This expansion continues even today. As the universe cooled, the first elements, mostly hydrogen and helium, began to form. Over vast stretches of time, gravity, the universe's master sculptor, pulled these elements together, forming colossal clouds of gas and dust. These are the birthplaces of stars, cosmic nurseries where new suns are ignited. Within these stellar nurseries, heavier elements were forged in the fiery furnaces of dying stars. When massive stars reach the end of their lives, they explode in spectacular events called supernovas. These explosions scatter the elements they've created, including the very elements that make up our planet and even us across the cosmos. This, in essence, is the Stardust from which Earth was born. Our own solar system began its life about 4.6 billion years ago within one such cloud of gas and dust in the Milky Way galaxy. Imagine a vast swirling disk of hydrogen, helium, and traces of heavier elements. The remnants of countless generations of stars that lived and died before our sun was even a glimmer. This is what we call the solar nebula. Gravity, that relentless force, started to pull this nebula together. As the cloud contracted, it began to spin faster and faster, much like an ice skater pulling in their arms. This spinning motion caused the nebula to flatten into a disk, with most of the material congregating at the center. At the heart of this swirling disk, the pressure and temperature became so immense that nuclear fusion ignited. This is the process where atoms are forced together to create heavier atoms, releasing enormous amounts of energy in the process. And just like that, our sun was born, a fiery giant that would come to dominate our solar system and provide the light and warmth necessary for life to eventually flourish on one of its tiny companions. But the story doesn't end with the sun's ignition. The leftover dust and gas in the protoplanetary disk was still in motion, colliding and clumping together. Think of it like cosmic dust bunnies sticking to each other. Over millions of years, these small particles gradually grew larger and larger, forming pebbles, then boulders, and eventually planetesimals, the building blocks of planets. Our Earth, along with the other planets in our solar system, was built from these very planetesimals. Through countless collisions and mergers, these smaller bodies accreted, their gravity pulling in more and more material. This was a violent and chaotic period, a cosmic construction site where worlds were being forged in the crucible of space. So, the next time you look up at the stars, remember that you're looking at the remnants of ancient stellar explosions, the very building blocks of our planet. Earth's journey began in these cosmic clouds, a testament to the power of gravity and the relentless processes of the universe. From these stellar ashes our world arose, a story we will continue to explore as we delve deeper into the intimate history of Earth. Welcome back to Earth, an intimate history. In our opening from the ashes of stars, we began our journey billions of years into the past, tracing the very origins of our planet to the vast expanse of the cosmos. Now, in Chapter 1, Stardust, We'll delve deeper into the cosmic cloud that gave birth to our solar system and eventually to Earth itself. The space between stars isn't completely empty. It's filled with what we call the interstellar medium, a very thin soup of gas, primarily hydrogen and helium, and tiny solid particles we know as dust. Think of it like the faint mist you might see on a very cold morning, but on an absolutely colossal scale. Over vast stretches of space and time, gravity, that universal force of attraction, can cause these wisps of gas and dust to slowly clump together. In certain regions, these clumps can become incredibly massive, forming what we call giant molecular clouds. These clouds are the true birthplaces of stars, immense nurseries where gravity works its magic. These molecular clouds are vast light years across and contain enough material to form hundreds, even thousands of stars. They're cold, dense pockets within the galaxy, shielded from the harsh radiation of nearby stars, allowing gravity to slowly but surely do its work. But a molecular cloud doesn't just spontaneously collapse to form stars. It usually needs a trigger, a cosmic nudge to overcome its internal pressure. One common trigger is the shock wave from a nearby supernova. Remember those massive star explosions we talked about? When a star dies in a supernova, it sends out a powerful ripple through space, like a pebble dropped into a still pond. This shock wave can compress parts of a molecular cloud, making them dense enough and initiate a runaway collapse. Another trigger could be the gravitational influence of a passing star, or even the collision of two molecular clouds. Once a region within a molecular cloud begins to collapse, gravity pulls all the surrounding gas and dust inwards. As this material falls toward the center, it starts to spin, slowly at first, but as it contracts, it spins faster and faster. This is due to a fundamental principle of physics called the conservation of angular momentum. Imagine that ice skater again. When they pull their arms in, their spin increases. The same thing happens with a collapsing cloud of gas and dust. This spinning cloud flattens out into a disc-like structure. At the center of this disc, where most of the mass accumulates, the pressure and temperature begin to skyrocket. This central region is the protostar, the baby sun, not yet fully ignited. As more and more material falls onto the protostar, the temperature and pressure in its core eventually reach a critical point. This is when something truly remarkable happens. Nuclear fusion begins. But the story of our solar system doesn't end there. Surrounding the newly formed sun is the rest of the flattened disk, the protoplanetary disk. This disk is made up of the leftover gas and dust, the raw materials for the planets, moons, asteroids and comets that make up our solar system. Why, this disk contains a vast array of elements, not just hydrogen and helium. Remember those supernovas? They enriched the interstellar medium with heavier elements like carbon, oxygen, iron and silicon, the very elements that will eventually form the rocky planets, including our Earth. So when we talk about stardust, we're not just being poetic. The atoms that make up our bodies, the air we breathe, the water we drink, and the very ground beneath our feet were all forged in the hearts of ancient stars that exploded billions of years ago. Our solar system and everything within it is literally made of recycled stardust. The formation of our solar system from this swirling cloud of stardust was the first crucial step in the long and incredible journey of Earth. In the next chapter, we'll explore the violent birth of our planet itself, as these tiny particles in the protoplanetary disk began to collide and coalesce, eventually forming the molten world we now call home. In the previous chapter, Stardust, we witnessed the birth of our solar system from a vast cloud of gas and dust. Now, the cosmic construction site is in full swing. Our focus narrows to one particular clump of matter, relentlessly growing larger, hotter, and more violent than anything we can truly imagine today. This is the story of the early Earth, a world shrouded in fire, the age of the molten Earth. The accretion process, that gradual sticking together of smaller bodies, continued with immense intensity. For tens of millions of years, the young Earth was a cosmic target, constantly bombarded by leftover debris from the solar nebula. Each impact, from tiny dust grains to massive planetesimals miles across, added to Earth's growing mass. But these collisions weren't just adding bulk, they were also generating incredible amounts of heat. The kinetic energy of these impacting bodies was converted into thermal energy upon impact, causing the early Earth to heat up dramatically. Think of it like repeatedly hammering a piece of metal. It gets hotter with each strike. And the impacts weren't the only source of this primordial inferno. Within the Earth's growing interior, radioactive elements, remnants from those long-dead stars, were also decaying, releasing their own heat. This internal furnace further contributed to the rising temperatures within our nascent planet. The combined effect of these relentless impacts and internal radioactive heating pushed the early Earth past a critical threshold. The entire planet, from its surface to its deep interior, became molten. Imagine a global ocean, not of water but of incandescent rock, a magma ocean. This magma ocean wasn't uniform. Differences in density meant that heavier elements like iron and nickel began to sink towards the Earth's center under the influence of gravity. This crucial process, known as planetary differentiation, was the birth of Earth's core. Surrounded by this dense metallic core was the vast mantle, also molten rock, but composed of lighter silicate minerals. And on top, a thin, fragile crust began to form as the outermost layers started to cool and solidify, only to be repeatedly broken apart and remelted by further impacts. This fiery picture was further complicated by one of the most significant events in Earth's early history, the impact with a protoplanet we call Theia. This colossal collision, we believe, not only led to the formation of our moon, but also added a tremendous amount of energy to the already molten Earth, essentially resetting the clock on its cooling process. Even in this incredibly hostile environment, the Earth was beginning to exhale. Volcanic activity, driven by the immense heat within, released vast quantities of gases from the molten interior into the atmosphere. This early atmosphere was likely a toxic brew, dominated by water vapor, carbon dioxide and nitrogen, with little to no free oxygen. But despite the presence of water vapor in the atmosphere, liquid water couldn't yet exist on the Earth's surface. The temperatures were simply too high. Any water that condensed would have immediately boiled back into steam. The Earth was trapped in a fiery embrace, a world utterly inhospitable to life as we know it. This was a time of immense geological upheaval, a period of constant change and violent activity. The molten Earth was a dynamic system, constantly churning and reshaping itself under the influence of heat and gravity. It was a far cry from the stable, life-giving planet we inhabit today. Yet, within this fiery chaos lay the seeds of our future world. The differentiation into core, mantle and crust was a fundamental step. The outgassing, while creating a toxic atmosphere, was also laying the groundwork for future oceans. Slowly, imperceptibly at first, the molten Earth would begin its long journey towards cooling and solidifying. The age of the molten Earth was a crucial chapter in our planet's story, a necessary stage in its evolution. It was a time of intense heat and geological transformation, setting the stage for the next dramatic act, the birth of the oceans. Join us in the next chapter as we explore how water, the very essence of life, finally arrived on our cooling planet. The early Earth, a fiery crucible forged in cosmic collisions, was slowly beginning to relinquish its intense heat. The magma ocean, while still vast and turbulent in places, was starting to solidify, forming a more stable, though still young and fragile, crust. But for our planet to truly become the blue marble we know, it needed one crucial ingredient: water. This is the story of the birth of Earth's oceans. One of the primary sources of Earth's water lies deep within the planet itself. During the intense volcanism of the early Earth, as molten rock rose to the surface, it released trapped gases. Among these gases was water vapor steam, which billowed into the young atmosphere. This process, known as outgassing, was a continuous contribution of water to the planet's surface environment. As the Earth continued to cool, the atmosphere also began to change. The intense heat that had kept all water in a gaseous state started to dissipate. Eventually, the temperature dropped low enough for the water vapor in the atmosphere to condense, forming clouds. And from these clouds, the first rains began to fall, a relentless downpour that would have lasted for millennia. This primordial rain carved out the early landscape, flowing into depressions and basins that had formed on the newly solidified crust. Over vast stretches of time, these basins gradually filled, giving birth to the first oceans. These weren't the vast interconnected oceans we see today, but rather smaller, isolated bodies of water scattered across the globe. But the story of where Earth's water came from is more complex than just internal outgassing. Scientists believe that a significant portion of our planet's water may have been delivered from beyond, carried by icy visitors from the outer solar system. In the early solar system, beyond the orbit of Mars, lay a vast reservoir of icy bodies, comets and water-rich asteroids. These celestial wanderers were frequently perturbed from their orbits by the gravitational influence of the giant planets, sending them on collision courses with the inner solar system, including our young Earth. The evidence for this cosmic delivery comes from the very composition of Earth's water. Scientists analyze the isotopic ratios of hydrogen, the relative amounts of regular hydrogen and its heavier isotope, deuterium, in Earth's oceans, and compare it to the water found in comets and asteroids. Interestingly, the isotopic signature of water in some types of asteroids, particularly those from the inner asteroid belt, matches very closely with that of Earth's oceans. This suggests that these ancient space rocks played a crucial role in delivering a significant portion of the water that covers our planet today. While the contribution from comets is still debated, the evidence for asteroid delivery is compelling. These early oceans were a far cry from the clear, life-sustaining waters we know today. They were likely rich in dissolved minerals leached from the young crust and the atmosphere, potentially appearing greenish or even reddish in color due to the high iron content. While the birth of the oceans was a monumental step in Earth's evolution, it's important to remember that at this stage, life as we understand it had not yet emerged. The conditions were still harsh, with frequent volcanic eruptions, intense ultraviolet radiation from the young sun, and an atmosphere lacking significant oxygen. However, the presence of liquid water was absolutely crucial. Water is often called the universal solvent because it can dissolve a wide range of substances, facilitating chemical reactions. It provided a medium in which the complex molecules necessary for life could potentially form and interact. The birth of the oceans was therefore a pivotal moment, setting the stage for the next extraordinary chapter in Earth's history. The origin of life itself. The journey from a molten ball to a planet with vast oceans was a long and complex one, driven by the relentless forces of geology and the occasional delivery from the cosmos. Join us in the next chapter as we delve into one of the greatest mysteries of all. How did life arise from these primordial waters? With the birth of the oceans, our planet had acquired its defining feature, liquid water. But the Earth's surface was still a far cry from the familiar continents we know today. The crust, the planet's outermost skin, was thin and constantly being recycled by the immense heat within. Now, as the Earth continued its long cooling process, the first stable landmasses began to emerge from the global ocean. This is the story of the formation of the first continents. The early crust was primarily composed of dense, dark volcanic rock, similar to the basalt we see on the ocean floor today. But beneath this surface, the Earth's mantle was still incredibly active, with plumes of hot rock rising and falling, driving the first stirrings of what would eventually become plate tectonics, the engine that shapes our planet's surface. In certain areas, lighter, silica-rich rocks formed through volcanic processes and the melting of the early basaltic crust began to accumulate. These lighter materials were less dense than the surrounding mantle, making them buoyant and resistant to being pulled back down into the Earth's interior. These were the seeds of the first continents, small, scattered landmasses, often referred to as proto-continents or cratons. Volcanic activity played a crucial role in building these early continents. Eruptions spewed forth molten rock, which cooled and solidified, adding new material to the emerging land. Over millions of years, repeated volcanic events gradually built up these proto-continents, inch by painstaking inch. Around 4 billion years ago, a significant milestone was reached in Earth's history, the beginning of the Archean Eon. During this vast expanse of time, the Earth continued to cool, and the proto-continents became larger and more stable. While still very different from the continents we know today, these were the first substantial areas of land to break the surface of the global ocean. These early continents, though desolate and devoid of the lush vegetation we see today, began to interact with the atmosphere and the oceans. The relentless forces of weathering and erosion, driven by wind and rain, started to break down the exposed rock, releasing minerals into the surrounding waters. This early chemical weathering would have a profound impact on the composition of the oceans and the atmosphere over vast timescales. It's important to remember that at this stage life on land was still non-existent. The harsh ultraviolet radiation from the young sun, unfiltered by an ozone layer, made the land surface an incredibly hostile environment. Life, as we will explore in the next part of our story, was still confined to the relative safety of the oceans. These first continents, though seemingly insignificant compared to the vast landmasses we see today, were the foundations upon which all future continents would be built. They were the first permanent land to emerge from the global ocean, and they played a crucial role in shaping the Earth's climate and geology for billions of years to come. Over time, these early proto-continents would collide, break apart, and reassemble in a slow, majestic dance driven by the ever-active forces within our planet. The emergence of the first continents marks the end of our initial journey into the birth of our planet. From the swirling cloud of stardust to a world with oceans and the first land masses, the early Earth underwent a period of dramatic and transformative change. But the story is far from over. In Part 2 of Earth and Intimate History, The Quickening, we will delve into the next extraordinary chapter, the origin and early evolution of life itself in those primordial oceans.